All right. Good afternoon. Again, just going back to what we had encountered with absolute value equations, and we have for this particular case, we have on page 70, and we have here starting out with number 90. Okay, and we have in this expression, okay, we have 4 times the absolute value 2t plus 7, okay, plus 2 is equal to 22. And again, we're looking at solving for t, and we have in the process now we're going to isolate the absolute value of 2t plus 7. And again, with absolute value bars, we do not treat those as operation grouping symbols as would be the case with parentheses or brackets. So in other words, you're not going to distribute 4 over 2t plus 7. Okay, so we're going to work around the absolute value of 2t plus 7. And first part is that we can move the 2 that is added over to the other side, okay, by subtracting. So we're going to have, at this stage, we have 4 times, okay, the absolute value of 2t plus 7 is equal to 22 minus 2, which is going to be 20. And again, we're going to take care of the 4, not by distributing, but by dividing. Okay. So if I divide both sides of the equation by 4, so the left-hand side of the equation becomes the absolute value of 2t plus 7 and for 20 over 4. Okay, so 20 over 4, okay, that is equal to 5. And now, so I have the absolute value of 2t plus 7 equal to 5. And in terms of solving for t, I'm going to remove the absolute value grouping symbols. And just keep in mind, now we had the absolute value of x is represented by the absolute value of 2t plus 7. And for k, okay, k is supposed to be a non-negative value, and we do have k at 5. And now, upon removing the bars, I'm going to set 2t plus 7 equal to the numbers that have an absolute value of 5. That is, those numbers that will be 5 units away from 0. So one value is going to be 5 and the other negative 5. And so in looking at solving for t, I will set up 2 simultaneous equations with 2t plus 7 equal to negative 5, and also 2t plus 7 equal to 5. And for these equations, if I take 7 away from both sides to isolate 2t, so if we have negative 5 minus 7, this will be negative 12. For the other, for 2t, I have 5 minus 7, which will be negative 2. And we have with division by 2, we have that t is equal to negative 6. Also, t equal to negative 1. So we have a couple of solutions for t. Where we have at the lower end, we have negative 6. And at the upper end, we have negative 1. Now, for what we have for the next item, and this is with number 91, and I'm going from solving for t to solving for c. And in this one, okay, so we have negative 3 is equal to, and we have the negative, the absolute value of c minus 7, followed by the addition of 1. And, okay, so again, if I isolate the absolute value of c minus 7, So again, I'm going to have addition to undo. Just like I undid 2, I'm going to undo 1. Right. Now we have in number 91. Okay, so you have taking 1 away, okay, from both sides. Okay, so you have -4. And we have is equal to the negative of the absolute value of c minus 7. Okay. And what I can do here, now I have a negative constant, but if you notice we have a negative constant in front of the absolute value of c minus 7. So I can remove this negative, and I can either multiply or divide the equation by -1. So I'm going to have in the rewrite. Okay, so I have that 4 is equal to the absolute value of c minus 7. And what I'm going to do here, I'm just going to switch the sides here. Just have the absolute value of c minus 7 on the left and 4 on the right. And now taking care of the absolute value bars. So if we go from the absolute value of c minus 7 to c minus 7, okay, I'm going to set c minus 7 equal to those values that will be 4 units away from 0. Okay, so again, if I have the absolute value of x equal to k, then that translates to x equals plus or minus k. So this will be c minus 7 is equal to plus or minus 4. So I will have here c minus 7 is equal to -4, and isolating, okay, if I add 7 to both sides in both equations, so for c minus 7 equal to -4, we're going to have that c is equal to -4 plus 7, which will be 3. And for c minus 7 equal to 4, adding 7, so we have c is equal to 4 plus 7, which will be 11. So just like t earlier, c is going to have 2 solutions, and this time they will both be positive, that we have at 3 as well as 11. Now I just mentioned, in a way you can go back and check your result, and that's just a, if you just follow, that's just like to safeguard against like having follow through, like botching the algebra somehow or other. But in terms of the level of double checking, it's not as intense as it would be if you had like even root radical equations, especially if you forgot the idea about the principal square root rule along the way. Now, in what we have with number 93, okay, here we have an absolute value equation. This time around, where upon we have 2 is equal to 8 plus the square root, 2 plus the absolute value, and we have of 11y plus 4. Okay, and so I have the absolute value term on the right hand side, and if I get it by itself, so I'm going to move the constant 8 over. So subtracting 8 from both sides. Okay, so I have 2 minus 8, so this will become -6. And we have that -6 is equal to the absolute value of 11y plus 4. And what I'm going to do here, just like what I did with the absolute value of c minus 7 and 4, I'm just going to switch the sides here. Kind of like going like b is equal to a is equal to b. Still the same logic equivalent. So absolute value of 11y plus 4 is equal to -6. And if you notice, okay, we have absolute value of x is represented by the absolute value of 11y plus 4, and k is represented by -6. Okay, and the problem here is that what we have to represent k should be a non-negative value. And since we have -6, which is not allowed for k because of the negative sign, we have automatically that for y there's going to be no solution. So in other words, kind of go back to so here k cannot be negative. If I had a +6, I would have the ability to follow through. All right, now for number 94, okay, so you have 6 is equal to, and we have 7 plus the absolute value of 9z minus 3. Okay, and just a little bit of history to repeat different numbers, but same kind of follow through because the setup is almost identical. You have a constant absolute value term, you have a constant absolute value term, and here to get the absolute value expression by itself, I'm just going to move this 7 over, and here we have 6 minus 7, which would be -1. To the right, 7 is go out, and I have equal to the absolute value of 9z minus 3, and just switching the order. So the absolute value of 9z minus 3 is equal to -1, and again we have absolute value of x represented by that of 9z minus 3, and k is represented by -1, and again k cannot be negative, and so right away there's no solution for z. Now, for what we have in the next item, okay, this one kind of sort of tricky. For we have not one but two absolute value expressions, and in number 96. Okay, we have for the first absolute value term, okay, we have the absolute value of 2a minus 3 is equal to the absolute value of a plus 2 and for what we have here for the absolute value of 2a minus 3, now again there'll be two quantities that will have an absolute value of 2a minus 3. One is going to be 2a minus 3 and the other is going to be the negative of 2a minus 3. So I'm going to take the positive and negative of the quantity of 2a minus 3. And for a plus 2, then we have positive and negative quantity of a plus 2. Okay, and the way to go about this, I'm going to do here, I'm going to stick with just the positive of 2a minus 3. So I can set up a couple of equations. One is linking both positives together, and the other, if I keep the positive of 2a minus 3, I can set up another equation where I can set this equal to the negative of a plus 2. So I can have up to 4 equations, but I need only 2. And I'll show you why. So right now we have 2a minus 3 corresponding to the positive of the quantity of a plus 2. Again, have positive 2a minus 3 equal to the negative of a plus 2. But now I'm just going to mention, if I took the negative of the quantity of 2a minus 3, equal to the positive of the quantity of a plus 2, what would happen here is that if I were to try to work these out, these would be just repetition of the solutions I would obtain in A from these first two equation setups. It could work all four, but you're going to have, two solutions, and if I work out all four equations, you're going to have the same two solutions repeated. Okay, and so we have in the mix. Okay, so if I take,
didn't get that. Could you try again?
Sorry, Siri. Okay, so if I take what I have here. Okay, so I have with.
No need to apologize.
Sure. Oh, don't you just love technology? All right, so you have in this one. All right, so removing the parentheses. Okay, so you have 2a minus 3 is equal to a plus 2. Okay, so if I look at this one, so you have 2a minus 3 is equal to a plus 2. And combining the variable terms together, so I can just take out a. So you have 2a minus a becomes a minus 3 is equal to 2. And if I add 3, okay, so I have a is equal to 5. Now for what I have here, okay, so if I take out the parentheses, so I have 2a minus 3. And for the distribution of the negative over a plus 2, so we have negative a minus 2 okay, now in this one I'm going to combine the a terms. Now this time the smaller a term is negative a as opposed to positive a. Okay, so here we have 2a plus a becomes 3a minus 3 is equal to negative 2. And adding 3 to both sides, okay, so you have 3a is equal to 1, and with division by 3, so we have a is equal to 1/3. And let me kind of mention here, okay, so if I had, like with a at 5, okay, so 2 times 5 is 10, minus 3, so this would be the absolute value of 7. 5 plus 2 is 7, so absolute value of 7. And 7 is equal to 7. Now for 1/3, let's break this down a little bit more. So we have here, so 2 times 1/3 is 2/3 minus 3. 1/3 plus 2. Now for 2, I can just go ahead and write this as a fraction with 3 on the bottom. Okay, 2 over 1, 6 over 3. And 3 is going to be 9/3. 1/3 plus 6/3 is 7/3. Now 2/3 minus 9/3 is a negative 7/3. Now it's true that negative 7/3 and 7/3 are not the same, but they will have the same absolute value. Absolute value of a negative is a positive. Absolute value of a positive is still a positive. So we come out to the absolute value results where both will reduce to 7/3. Okay, so your two solutions for A will be 5 as well as 1/3. And if you worked out these other two equations, you would still come out to 5 and 1/3 again for A. Okay, now for what we have in the next phase, we have what will be regarded as equations that are going to have fractional exponents. And we have here we just sort of take a subset of this, okay, where we have equations with non-integer exponents. I might have already mentioned this introductory part. We're just sort of resetting. Okay, so we have with equations with non-integer exponents. Again, we have an exponential base a to the m over n degree is equal to the nth root of a to the m. Okay, so if I have like a fractional exponent, and I'll rewrite as a radical, is the denominator that indicates the type of radical that will be dealt with. And just in the case of examples, okay, if I have rewriting as a radical, and if I have something like x to the 3 halves, again, so the 2 is in reference to n, and the type of radical is going to be a second root. And of a to the m, this will be represented by x to the 3rd. And again, second roots, you don't see the number 2 for those types of radicals. We're looking at square roots. So x to the 3 halves will become x to the 3 halves, which will be the second root of x cubed, which reduces to the square root of x cubed. And if I have, let's say, y to the, let's say I have y to the 4/3, okay, this is going to become the cubic root of y to the 4th. And let's say that if I have something like z to the 5/8, okay, so your n value is going to be at 8, and a to the m would make reference to z to the 5th. Okay, so this is just translating from non-integer powers to their radical equivalents. And now where equations are going to come into the scene. And let's say that if you're looking at solving for x, and we'll say we have here okay, we have the x to the 1/2 is equal to 8. Okay, and just going to add in this little extra step. So again, you have x to the 1/2. You have the second root of x to the 1st is equal to 8. And again, so that's just the square root of x is equal to 8. Okay, now You got an even root radical expression set equal to a constant, and for there to be a solution, again, the even root radical expression must reduce to a non-negative constant, and 8 is positive. So we have a solution, at least a solution for x. So I can free up the radical upon squaring both sides. And we have the square root of x squared. Okay, so this will become x. And 8 squared is going to be 64. And again, you have like the square root of 64 is 8. And for what you have in terms of the overall picture, if you were to put in your calculator, you have like 64 to the 1/2. Do not forget to put the 1/2 in parentheses. So you have 64 to the 1/2 degree with 1/2 in the parentheses, and it has to be in parentheses. You have equal to 8. Now, and let's say that if we have a situation, and we'll say that we have 3 times 2x plus 2. Now say we have to the 1/3 is equal to 12. Okay, now for this one, if I'm solving for x, I can just isolate the variable or exponential expression, especially since 3 will go into 12 completely, so I'm just going to divide the equation by 3. So for what I'm going to have now, say I have the quantity of 2x plus 2 to the 1/3. Okay, and I have 12/3 goes to 4. Now, taking what I have now, okay, so I have a single term with a non-integer exponent. And again, if I go from non-integer exponent to the radical equivalent, so this will become the cubic root of 2x plus 2 is equal to 4. And okay, so again I have the cubic root of an expression set equal to 4, and I can take care of the radical. Just as I square it out to get rid of the square root, I'm going to cube out to get rid of the cubic root. So for what I have on the left, okay, so we have 2x plus 2 is equal to 4 cubed, and 4 cubed is going to be 64. Taking 2 away from both sides. So that 2x is equal to 32, and with division by 2, okay, we'll come out to x is equal to 31. All right. And for what we have, let's say, okay, and let's say that if we have let's see, let me kind of give you a little bit of a transition here. Let's say you have x minus 5 to the 1/2, okay, is equal to -7. Okay, again, if I go from exponent to radical, okay, so we have the square root of x minus 5 is equal to -7. Okay, now again, I'm dealing with an even root radical, and we have with the principal square root rule. Now the even root of an expression cannot reduce to a negative constant. And because we have a minus 7, okay, there's going to be no solution. But now, if we had, again, for x minus 5 to the 1/2 equal to positive 7. Okay, again, just once again, so if I have the square root of x minus 5 equal to 7, now again, square root of x minus 5 cannot reduce to a negative, but it can reduce to a positive. So I can continue. So we have with the square root of x minus 5 I can square both sides. And the square root of x minus 5 becomes x minus 5. And 7 squared becomes 49. And again, if I isolate x by adding 5 to both ends, and so for this outcome, we're going to have that x is equal to 54. And let's say that, okay, now where the principal, not just the principal square root rule, but where the square root property of equality can come in. And we'll say that we have, for instance, let's say we have x minus 6, okay, to the 2/3 is equal to 4. Okay, now for what we have at the stage, okay, so this time I have 3 on the bottom. Okay, so this will signal that the type of radical we are dealing with is going to be a cubic root. Okay, so you got the cubic root of the square of x minus 6, okay, equal to 4. Now the work is going to get a little bit crowded because here, after writing as a radical, okay, if you notice, I squared both sides to get rid of the square root, say in the fourth case, but now to get rid of the radical, I'm now going to take both sides and cube out. So for what I'm going to have here, okay, so you have the radical and the exponent will just undo each other. And I'm going to have x minus 6 squared to be freed up. So we have 4 to the 3rd. We've got 4 times 4 times 4. This will be 64. Now, at this juncture, okay, so you had the square of an expression set equal to a constant. And if you recall, we have worked with the square root property of equality. Like we had the square of an expression equal to a constant that is non-negative. We had the x is equal to plus or minus the square root of p. So we have here with the square of x minus 6 representing the square of x. If I go from second order to first order. So we had the x minus 6 is equal to plus or minus the square root of 64 So we have the x minus 6 is equal to plus or minus 8. Okay, so with x minus 6 equal to negative 8, if I isolate the x, so we'll have adding 6 to both sides. So for x minus 6 equal to negative 8, we have that x is equal to negative 8 plus 6. Okay, so that is going to be at negative 2. And for x minus 6 equal to 8, if I add 6 to both sides, so we're going to have that x is equal to 14. So we're going to have a couple of solutions for x with minus 2 as well as 14. And let me mention this. If we have, let's say, and we'll say that we have 3x minus 2, and say we have to the 3 halves is equal to 27. Okay, so if I go from exponent to radical, okay, so here I'm going to have the square root of 3x minus 2 to the third is equal to 27. Okay, so again, I'm going to have a couple of operational ways of following through. First of all, after the rewrite, I'm going to square both sides. Okay, so as to get rid of the square root. Okay, and if I square both sides, okay, so I'm still going to have 3x minus 2 to the third left over. And we have 27 squared. Okay, so 27 times 27, this will be 729. Okay, now for 3x minus 2 raised to the third equal to 729. Okay, now if you notice, we had used the square root property of equality, but that's when we had the square of the binomial. But now that I have the cube of a binomial, instead of using the square root property of equality, I'm just going to take the cubic root of both sides. Okay, so if you notice, I took the exponent to eliminate the radical. Now I'm going to go in the other direction, because what was freed up was the cube of 3x minus 2. And to undo that cube, I'm going to take the cubic root Okay, so you have the cubic root of 3x minus 2 raised to the third. Okay, so this will be 3x minus 2. And for the cubic root of 729, okay, 729, another one of the numbers that will happen to be both a perfect square and a perfect cube. And the number times itself, that will give you 729. Okay, that is going to be at 9. And for 3x minus 2 equal to 9. Okay, so if I add 2 to both sides, so we have that 3x is equal to 11. And we have with division by 3. Okay, it's going to result that the value we have for x is going to be a non-integer, where we have 11/3. All right. Okay. Now, in terms of looking at solving for x, I tell you what. For what we have with these two items, you look sort of similar to each other, but they are nonetheless distinct. And tell you what, just for the next few moments. Okay, let's see what we get for x. Whereupon we have 2 times the quantity of x plus 5 to the 2/3 is equal to 18. And also whereupon we have the quantity of 2x minus 2 to the 3/2 minus 3 is equal to 5. Okay, if you're still working on these items, that's okay. Now we're looking at solving for x in each of these items, and first of all we have 2 times, okay, the quantity of x plus 5 raised to the 2/3, okay, is equal to 8. And okay, now what I can do is I can isolate x plus 5 to the 2/3 upon dividing by 2 on both sides. Okay, so for what I have on the left, okay, so I have x plus 5 raised to the 2/3 is equal to 9. Okay. And in terms of following through, so if I take what I have here, okay, so for x plus 5 to the 2/3, if I express as a radical, okay, so again the denominator dictates what type of root there will be once the expression is laid out in radical terms. So we're going to have a cubic root, and this will be the cubic root of what? Well, it'll be x plus 5 raised to the 2nd. And again, we have this equal to 9. Okay, now that I have written in terms of a radical, now I want to free up what's inside this radical, and the way to do so is to cube both sides. I know that the numbers are getting a bit crowded, but for what we have in the process, okay, so again, isolate the exponential term, wrote as a radical. Now I want to get rid of the cubic root, so to both sides I'm going to cube out. So think of like the radical and the 3 going out, and so what is inside, okay, is going to be freed up. So we have the square of x plus 5 is equal to, and 9 cubed, we have again 9 times 9 times 9, so this will be 729. And for the square of x plus 5, again, because I have an expression to the 2nd power equal to a constant, again I can go with the square root property of equality as one pathway. So we have with the square of x represented by the square of x plus 5 and p represented by 729. So I can go from 2nd to 1st order in x plus 5. And for plus or minus the square root of p, and we have plus or minus, okay, the square root of 729. So you got x plus 5 equal to plus or minus, and let me just mention, now we have with 729, okay, just on a same parallel, 729 is like 27 times 27 so you're looking at the square root of 27 squared. and it's like the 2's to take care of each other, so this would just go out to 27. So now, so you have plus or minus the square root of 729, which would be plus or minus 27. And for what we have with the equation, so we have at the lower end, we have x plus 5 is equal to negative 27. And at the upper end, we have x plus 5 is equal to 27. And taking 5 away from both sides in both equations. So if x plus 5 is equal to negative 27, we have x equal to negative 27 minus 5, which would be negative 32. And if x plus 5 is equal to 27, we come out to x is equal to 22. So there'll be a couple of solutions for x with negative 32 and positive 22. All right. Now in the case of what we have with our second item, okay, notice we have the exponents between the exercises happen to be reciprocals of each other. Okay. Now I'm going to isolate the exponential expression, so I'm going to move this 3 over. So we now have the quantity of 2x minus 2 to the 3 halves is equal to 5 plus 3, which is going to be at 8. Okay, notice before I had 3 on the bottom, 2 at the top. Now it's the other way around. Okay, so this time the 2 is on the bottom, and it's going to dictate that the type of radical is going to be a square root. And the square root of what? It will be the square root of 2x minus 2 quantity raised to the third. And we have is equal to 8. Okay, now before I had a cubic root, and I got rid of the radical upon cubing. Now I have the square root as the radical, and I'm going to get rid of that by squaring both sides. Okay, so I have with what is laid out. Okay, so squaring out to eliminate the radical. Okay, left hand side, we have left over. Upon removing the radical, we have the cube of 2x minus 2. To the right, okay, so I have 8 to the second, or 8 times 8, which is going to be 64. Okay, now for 2x minus 2 raised to the third. Okay, now if you notice, okay, when we had like an even power, like x plus 5 to the second, it was kind of considering that you had positive and negative values in the mix on the basis of the square root property of equality. Whereas with odd roots, you don't have to worry about pluses and minuses. You just take the radical of both sides. That will eliminate the exponent. Okay, so in this case, that which will eliminate the cube is going to be the cubic root . Okay, so for what I have on the left, okay, so the cubic root is going to eliminate, okay, the cube, to which we have as the exponent for 2x minus 2. Okay, so the 2x minus 2, that's going to be freed up, and that is going to be equal to the cubic root of 64. Again, we have the cubic root of 64. Okay, Now 64, that's like 4 times 4 times 4. Or the cubic root of 4 to the third power. Like the cubic root and the cube cancel each other. So this will go to 4. So the cubic root of 64 goes to 4. And we have with our two-step linear equation. So we have 2x minus 2 is equal to 4. And we have with isolating the variable term upon adding 2 to both sides. So we're going to have 2x is equal to 6. And we have with division by 2. So we have that x is equal to 3. All right. Okay. So for these items, okay, we're working with the real number system exclusively. And now, for what we have in the next item, we're going to maintain the use of radicals and many of the same operation that we have worked with throughout Chapter R, but we're going to be crossing over into what's referred to as the complex number system, and it's also referred to as the system of imaginary numbers. But I'm kind of hesitant to say imaginary numbers because there are some real-life applications to complex numbers. Like in physics, you have like positrons, and also there are some electrical engineering or electronics applications that do involve calculations of such nature, and they happen to involve complex numbers. And okay, now in terms of complex numbers, okay, we have at the root, or at the foundation. Okay, the centerpiece is going to be, some books will have it as the letter J, but most will have the letter I. And the letter I is going to be in reference to the square root of -1. And from the foundation, I is equal to the square root of -1. And especially when you're looking at operations between complex numbers, you might run into I squared, which is going to translate to -1. And let's say that if you have with complex numbers, just to kind of give you a feel for this, so if you have like reducing in terms of the letter I, okay, now say we have just numbers that we have here. Say have reducing in terms of the letter I. Okay, if I have, I'll start out with the negative of a perfect square number. So I have the square root of -25, and I can sort of detach the 25 and the negative sign. So I can have like the square root of 25 times the square root of -1. Now the square root of 25 is going to be 5. And again, I is equal to the square root of -1 and vice versa. So you got square root of 25 is 5, and the square root of -1 is going to be I. So we have, in reduction terms, the square root of -25 becomes 5i. Now let's say that if I have something like the square root of -18, okay, now here, okay, so we will have the square root of 18 times the square root of -1. Now, unlike 25, 18 is not a perfect square number. Okay, however, we have for the square root of 18, okay, so this will go to the square root of 9 times 2. Okay, so 9 is the highest perfect square that will go into 18, so you have the square root of 9 times, okay, the square root of 2. And we have, I'll just do this at the end, have times the square root of -1. So you have square root of 9, okay, so that's going to be 3. And you have times the square root of 2, Square root of negative 1 becomes I. And another way that this could be possibly displayed would be to just have the radical at the end. So you could write this as 3I times the square root of 2. And let's say that also in terms of the letter I. If I have the square root of negative 500, so I have like the square root of 500 times, the square root of negative 1. Now 500 is not a perfect square value, but it can be reduced because the highest perfect square they'll go into 500 is going to be 100. Now the square root of 100 is going to be 10. Then we have times the square root of 5. And we have times the square root of negative 1, which is going to be I. So we have 10I also has the possible display for the reduced result. Okay, and let me mention something. Like if you didn't pick out the highest perfect square value, I'm just going to kind of mention this. You had the square root of negative 500 square root of 500 times the square root of negative 1. And let's say that if you had say if you didn't think of 100 but you thought of, let's say, like 25. You have like the square root of 25 times 20 times the square root of negative 1. So you got the, 25 is a perfect square number. And guess what? For 20 would factor out to 4 times 5. And 4 is a perfect square number. So if you were to partition out, you got the square root of 25 times the square root of 4 times the square root of 5. And the square root of negative 1, we can just write that as I. Square root of 25 is 5. Square root of 4 is 2. We got the square root of 5. And you still come out to the same result. 10 square root of 5 times I, or 10I times the square root of 5. Okay. Yeah, so if you don't start out with the highest divisible perfect square, but the next highest, it can still reduce and still come to the final destination. A little longer pathway, but still another correct but longer pathway. All right, and now for complex numbers, we're going to have what's referred to as the standard form of a complex number. Okay, and that's going to be A plus BI. Okay, just to restate, so again, I is equal to the square root of negative 1. And we have that I squared is equal to negative 1. Okay. And let's say that if you're looking at complex numbers, and are trying to write in terms of the standard form, and we'll say that we have at the start, okay, say we have 3 plus the square root of negative 36, and say we have plus the quantity, and we'll say we have 2 plus the square root of negative 25. Okay, so just taking what we have now for 3 plus the square root of negative 36. Now, 36 square root of that is going to be 6. Now, for negative 36, okay, that is going to be 6i. So 33 plus 6i. We have plus, like the quantity, so we got 2 plus, and the square root of negative 25. Okay, that's going to be 5i. And once I take out the parentheses, so I'm going to have 3 plus 6i plus 2 plus 5i. And combining, okay, so representing a, we have the sum of 3 and 2, which would be 5. And for the bi terms, we got 6i plus 5i. And so we're going to have 11i. So the end result here is going to be 5 plus 11i. Also, if we have, say, the operation of multiplication involved, and we'll say that we have the square of 3 minus 2i. Okay, so for the square of 3 minus 2i. Okay, so this will reference 3 minus 2i times itself. Now, while we are dealing with complex numbers, okay, we can still apply the FOIL. Okay, so you have 3 times 3, first product is 9. And you got outside product, we're going to have negative 6i. Inside product, we have negative 2i times 3, so we have another negative 6i. Last product, this is where you had to be careful. Now we have a negative times a negative is a positive. I times I becomes I squared. Okay, now we have I is equal to the square root of negative 1. And guess what? I squared is equal to negative 1. And your standard form does not have an I squared in it. So that means that to get rid of any raised powers, you consider that I squared is equal to negative 1. So you got 9, and we have negative 6i minus 6i. We can say we have minus 12i. Then you got plus 4i squared, but again, that's going to be 4 times negative 1. So you got 9 minus 12i. 4 times negative 1 becomes negative 4. And for this end result, now your A value, you have 9 minus 4, so you have 5 once again. And for your BI, your B value is going to be a negative constant, so that's going to be a negative 12i. So in this format, we have 5 minus 12i. And say just for this last case. Now I think Alex allows both forms, but in case if it doesn't, if you have a difference of squares, so you have the quantity of 7 minus 3i times that of 7 plus 3i. And if we were to FOIL out what we have here, so we have, again, so you have 7 times 7, so this would be 49. Outside product, okay, you have 7 times 3i, so you have a positive 21i. Inside product, you have negative 3i times 7, so this would be a negative 21i. Last product, we have negative 3 times 3 is negative 9. I times I becomes I squared. So we're back to that I squared once again, and again, we have I squared is equal to negative 1. And for what we have in following through, okay, we've got 49. Now 21i minus 21i, those I terms will cancel out. Now we got minus 9. And I squared, again, we have at negative 1. So we have 49. Now negative 9 times negative 1, that will be a positive 9. And 49 plus 9, this comes out to 58. And notice we don't have an I term since positive and negative 21i cancel each other out. But if you had to do more than just show the A value, which is non-negligible for 58, if there was any one other way to display this, if I had to show the I term, this would end up being like 58 plus 0i. And that's just to get the I term to show up. And 0i is still negligible. All right. Okay, so we're going to be looking into complex numbers, and we'll be looking at a lot of similar stuff with like fractions, FOIL method, all that other stuff, like what we had dealt with the real number system, but also working with the letter I.